So we are to talk about the refrigerants in today's lecture. So refrigerants are the working fluid in a refrigeration system, or it can be a heat pump system also. And as pointed out earlier, the working fluid which might be preferable can be air or water because they are easily available and they are most eco-friendly chemicals to work with. But then there are certain difficulties with use of water as well as air. The thermodynamic properties of these substances are not suitable for most of the application, except a few niche applications. So though we are having a chapter on air refrigeration cycle, the application of that is very limited. And in common day-to-day life, or for vast majority of the applications, they are not suitable. Water is also used as a refrigerant, but not in vapor compression refrigeration systems, but in vapor absorption refrigeration systems, as it will be talked about later. So we will be talking about the other chemicals which are suitable as refrigerants. And actually this field has become very dynamic due to various considerations, and those considerations are continuously changing. And because of that, the refrigerants which were used earlier in the intermediate period, they become unfavorable, and now they are again becoming favorable. Right, so we'll be looking at this dynamic scenario a bit also. So refrigerants can be categorized as primary and secondary refrigerants. Primary refrigerants are the working fluids in refrigeration, air conditioning, and heat pumping systems. They absorb heat from one area, such as air conditioned space, and reject it to another, such as atmosphere, usually through evaporation and condensation respectively. So now you know about the vapor compression refrigeration system, which is the most common or most dominant system in the field of refrigeration. And in this system, on one side, when the heat is absorbed from the space or the product, there is evaporation of the refrigerant, and on the other side, the heat is rejected by condensing the refrigerant. And this is what happens in the primary circuit, which has the components like compressor, condenser, throttling device, and the evaporator. So these phase changes occur both in absorption and mechanical vapor compression refrigeration systems, but they do not occur in systems operating on a gas cycle using fluids such as air. So even air can be the primary refrigerant, but we'll have a separate discussion on that. In this chapter, we'll be mostly talking about the common refrigerants which are used in vapor compression refrigeration systems. Though ideally, COP of system depends solely on temperature limits. As per the reverse Carnot cycle thermodynamics calculations, it only depends upon the highest temperature and lowest temperature. But in the actual COP, the design of the system, size of the system, cost of the system, safety and serviceability, all these features also depend upon the refrigerant used in the system and the properties of the selected refrigerant. And then there can be another category of refrigerants called secondary refrigerants. They are just a medium. They do not flow through the compressor and the heat exchangers like condenser and evaporator, etc., and throttle valve, but they are just a medium to transfer cooling effect from one place to other, or from one component to another component. For example, chilled water is used for transferring cooling effect from chiller plant to air handling unit. Okay, so you have some idea about the water chilling plant where the primary refrigerant is R22, but the secondary refrigerant is water. Water is cooled with the help of the primary circuit of refrigeration. Water temperature is reduced, and that can be used in a unit called air handling unit, where the there is indirect contact between water and air, and with the help of that heat exchanger or chilled water coil, the enthalpy of the air is reduced, the air is cooled. So here the water is the secondary refrigerant, right? But then though water is a very good media for heat transfer and very popular in many of the chillers, and water chilling plants are very common, particularly in air conditioning systems. But the freezing point of water is 0 degrees Celsius. So if the application needs secondary refrigerant as well as sub-zero temperatures, then one may have to go for glycol, or one may have to go for brine. Brine is nothing but the solution of salt in water. So brine is used as secondary refrigerant in ice plants, which where ammonia is generally used as a primary refrigerant. So this is about uh, the two categories of refrigerant, primary and secondary. Though most of the discussion here is regarding the primary refrigerants only. Now, what is the selection criteria for refrigerant? What are the properties that you will consider? So the properties, those will be considered are thermophysical properties of refrigerant, thermophysical and thermodynamic properties of refrigerants. Then another one is environmental and safety properties, and the third is economics. So most of the times, finally, it's economics which drives many of the decisions. So let's talk about some thermodynamic and thermophysical properties of refrigerants. So one of the very important one is the critical temperature of the substance, and we talked about this a bit in the previous class also, where we talked about the transcritical cycle for carbon dioxide. So low critical temperature of refrigerant may be responsible for high condenser pressure, generally resulting in high cost of system because of need for thicker wall of tubes. So critical temperature, let's say we take an example of one of the very popular refrigerant R134A. So its critical temperature and is 101.06 degrees Celsius, while it is comparatively low for R32, which is another refrigerant which is common in becoming common in market. So that there the critical temperature is 79.11. So obviously R32 has low critical temperature, and because of that, if you say your condenser temperature is 50 degree Celsius, condenser or condensing temperature is 50 degree Celsius. So in that case, condenser pressure for R32 would be 3.14 megapascal or 31 bar, which is quite high. And R134A system, the pressure will be just 13.2 bar, right? So which means that R32 system will have to be designed for much higher pressures. So this is how the critical temperature of a substance affects the certain decision making in which refrigerant to use in which systems. And then the other one is normal boiling point. So it's the pressure at which the refrigerant boils. Sorry, it's the temperature at which refrigerant boils at atmospheric pressure. If NBP is less than evaporator temperature, say your evaporator temperature is -20 and the NBP is -40, right? So in that case, your evaporator will be at positive gauge pressure because you want the refrigerant to condense or rather evaporate in the evaporator. So there will be positive gauge pressure which can be maintained, which is generally desirable, right? You want to maintain certain positive gauge pressure in the evaporator. This is for most of the common cases, though it's not that evaporator will never have negative pressure. In certain applications, it might be so. Low NBP leads to higher evaporator pressure and lower specific volume of refrigerant vapor at compressor inlet for given application. Evaporator pressure is high, then the specific volume of the refrigerant coming out as vapor from the evaporator will be specific volume will be low, right? And because of that, the flow capacity of compressor will be high for such cases, and this will help to reduce specific compressor work, right? So you already know that the compressor work depends upon the specific volume. So specific volume is low, then the compressor work will be low. Then so one example is quoted here. Again, NBP for R134A is minus 26.07 degrees Celsius, while it is minus 40.81 for R22. So let's say the evaporator pressure for R134, say your evaporator temperature is minus 10 degrees Celsius. So in case of R134A, the pressure would be 2 bar, and for R22, because its NBP is low, the pressure would be 3.55 bar. So R22 will work at higher evaporator pressure for the same evaporator temperature. The specific volume of saturated vapors. So if you are dealing with R134A, the specific volume of the vapor would be 0.0996 at this pressure, 2 bar pressure, and minus 10 degree Celsius. And for R22, it is 0.0653 meter cube per kg, right? So because of lower specific volume, the compressor size of R22 can be smaller for the same mass flow rate of the refrigerant. So this is how NBP is going to affect the performance of the cycle. Now we talked about two things: critical temperature and normal boiling point. Normally, when the critical temperature is low, normal boiling point is low, and vice versa. Right? So these two requirements. So what you say is critical temperature should be high and normal boiling point should be low for very common applications. But then these two things would be opposing each other, and you have to take a call. You have to compromise how to between these two, right, to finally select the refrigerant. Nowadays, lower power consumption of compressor and compactness of compressor is considered to be more important, right? And condensers are many times designed with higher pressures. Now, the third one is latent heat of vaporization. This should be as high as possible to reduce mass flow rate of refrigerant for given capacity of the system, as most heat rejection and gain by refrigerant occur during its phase change. So latent heat of vaporization, let's say for R32, it's 331 kilojoule per kg, while it is very high, 1297 kilojoule per kg for ammonia. For water, as you know, it's one of the highest, right? Somewhere around 2400, 2500 kilojoule per kg. But at least in vapor compression systems, we are not able to use water, and ammonia is also having a high latent heat of vaporization, and this is one of the favorable properties. Right? So you have to you can have, for the same kilowatt capacity, you can have lower circulation rate for ammonia as compared to R32. Thus, the mass flow rate of ammonia would be much lower than that of R32 for the same capacity of the system, which reduces compressor displacement and size. Now, isentropic index of compression should be low for low temperature rise in the compression process. As you know that in the isentropic process or in the polytropic process of, so this can be polytropic index or isentropic index for a given refrigerant in the given temperature range. So if this index is low, then the temperature rise during the compression process would be low, which is desirable. So this value is 1.102 for R134A, while 1.166 for R22, right? So in case of R134A, you can expect a lower degree of superheating, while for R22, it will be higher. There will be more of superheating in case of R22, which you might have already witnessed in the experiments that were carried out in lab. Though there is no system with R134A, for R22, the degree of superheating is, you can say it was moderate, but in the winter, even in the winter time, it was moderate. So in summer, you can expect it to be much higher. Right? So this shows that mass flow rate is not the only criteria affecting the compressor work. The polytropic index also affects the compressor work. Then liquid specific heat of the refrigerant, that should be low to achieve higher subcooling temperature drop after condenser, resulting in less flash gas at evaporator inlet. So you already know that the refrigerant coming out of the condenser ideally is saturated liquid, but in actual practice there is always some subcooling, and many times a separate subcooler is also provided. Now if the liquid specific heat is low, then with the same heat removal you will get more temperature drop, which is desirable, and it will lead to less flashing of the vapor in the throttling device. Vapor specific heat should be high for lower superheating. Okay, so if you can recall liquid suction heat exchanger, which uses the vapor coming out of the evaporator to cool the liquid coming out of condenser. So here, if vapor specific heat is low and sorry, vapor specific heat is high and the liquid specific heat is low, what will happen is for the same heat exchange, the superheating will be less, but the subcooling will be more. Right? I'm not saying the number to be compared, right? So, uh, but for different refrigerants, if the liquid specific heat is low, the one which is having lower liquid specific heat would be preferable. And similarly, vapor specific heat, so one with high vapor specific heat would be preferred if you are comparing two different refrigerants. I'm not saying that the for the same refrigerant, whether the liquid specific heat should be higher than vapor specific heat or vice versa, right? That's the characteristic of that refrigerant itself. But we are comparing, if we are comparing two different refrigerants, then the favorable thing will be that the liquid specific heat is low and vapor specific heat is high. Then thermal conductivity should be high because it is taking part in the heat exchange process, right? And as you know, even in convection, the thermal conductivity plays an important role. So that's why the thermal conductivity of the refrigerant should be high, while surface tension and viscosity should be low to achieve higher heat transfer coefficient in heat exchangers. Higher heat transfer coefficient helps to reduce the size of the heat exchangers. Lower viscosity also helps to keep frictional pressure drops at low value, reducing compressor work. So these are a few thermodynamic and thermophysical properties which are considered while choosing a refrigerant. And finally, how the performance of the refrigerant depends upon all these properties which you will evaluate for a given temperature range or for given pressure range. You will evaluate the performance by simulating the cycle, and accordingly you will take a decision or choose a refrigerant. Of course, many of these are in a way theoretical things which are very important, very basic important properties, but there are many practical considerations many times, and you have to take those things also, those features also into account while choosing a refrigerant, a suitable refrigerant for a given system. So we talk about other important properties now, which in a way are not related with the performance or COP of the cycle, right? But from point of view of practical applications, they are very important. Right? So earlier we were not very much conscious about the environmental properties, But as the use of the refrigeration has become more and more common, when I say refrigeration, it also includes air conditioning, because air conditioning again most of the times is produced by use of a refrigeration system, vapor compression refrigeration system. So uh, as the use of refrigeration and air conditioning is becoming more and more common, and more and more people are using them, uh, the and there has been more awareness about the environmental issues. These properties have also become one of the very important properties which are investigated for a given refrigerant. So now we are talking about environmental and safety properties. Safety properties generally was always there on the cards. Like people used to understand generally the safety issues. Uh, okay, but environmental properties, that those considerations are comparatively new thing, which have become very important. So one of the important property is ozone depletion potential, called ODP in short. It is the measure of a material's ability to deplete stratospheric ozone, a value relative to that of R11 or R12, which is assigned a value of 1. This R11 and R12, though they are phased out now, were one of the most popular refrigerants used in the refrigeration systems. And it was found that they create damage to the ozone layer in the stratosphere, and a value of 1 ODP was assigned to these two refrigerants. They are found to be equally damaging, and the value of ODP equal to 1 was assigned to them. And the ODP of all other refrigerants is assigned values compared to this value. So now these were these were chlorofluorocarbons, right? Uh, but now with the use of hydrochlorofluorocarbon, HCFCs, right? So earlier it was only CFC. Then if there is an hydrogen atom in that compound, in that chemical, then it is called HCFC, hydrochlorofluorocarbon. So when chlorine is replaced with hydrogen, the effect of ODP is reduced quite a bit. So ODP for HCFCs like R22, R123 and R124 are, so for R22 it is 0.05. So you have seen that we in both the systems used in lab, still there is R22 used, and that's 0.05, the ODP, ozone depletion potential, much lower than R11 or 12, but still even this is considered to be objectionable, and these refrigerants will be phased out in future. For R123, it is even less, 0.02, and again same value for R124. And now it has been decided that the refrigerants with ODP 0 only will be accepted in future. So ODP for now, again there can be like HFCs, so there is no chlorine in that, right? So only fluorine and hydrogen. So for all those HFCs, the and hydrocarbons, the ODP is 0. So from point of view of ODP, all HFCs and HCs are acceptable. Now the next development, which is comparatively new as compared to the ozone depletion potential, is global warming potential. So it is an index describing the relative ability of the refrigerant to trap radiant energy compared to carbon dioxide. So carbon dioxide is assigned a value of GDP equal to 1. GWP of CO2 is thus 1, while it is now most of the refrigerants which are used today are having very high GWP, global warming potential, as compared to carbon dioxide. Now, the quantity of the carbon dioxide generated particularly in power generation or in vehicular emissions, uh, is very high. And comparatively, the use of the refrigerants is low. uh, but actually these chemicals are used in refrigeration system, and the use is becoming is increasing like very rapidly, and they are also used in or different other chemicals. So these values are very, but one may argue that the quantity is low. Then somebody may argue that so seems there was some issue with the connection, and it is restored now. So somebody may argue that the quantity used are less, and then somebody may even argue that they are working fluids used in closed systems, right? But even these closed systems have certain life, right? Limited life. So after that, if you don't recover it, it will go to the atmosphere, which is not desirable, and you cannot recover all of it. That is one part. Second, they at different stages during manufacturing, or while you charge the system, or like operation of the system, there are leakages occurring. So because of this, they are finally damaging the environment by contributing to the global warming. So for R22, the value, as you can see, is very high, 1700. For R134A, it is 1300. The hydrocarbons have comparatively low GWP, and there is one refrigerant which is comparatively recently developed, HFO 1234YF, which also has lower GWP. So now the trend is towards using refrigerants having not just zero ODP but also lower GWP, global warming potential. Now, just considering the global warming potential is not will not lead you to the right decision. So there is another property which is developed, and it is called parameter which is developed, and it is called total equivalent warming impact, TEWI, TEWI. This parameter is more holistic and considers the effect of direct emission of refrigerant. So when you say GWP, it is only talking about the direct emission of the refrigerant. Uh, but this TEWI also takes into consideration the indirect emission due to energy consumption of the system and CO2 emission due to the same. It may be noted that the comparison of refrigerant based on GWP and TEWI could give very different picture. Right? So it may be the case that the refrigerant has high GWP, but it gives very like thermodynamically it is very superior and provides you high COP. So in that case, your system will consume less power, and less power consumption means less requirement of power from the power plants which are producing CO2. So you should consider the CO2 emission throughout its life, right? And also the effect of the direct emission. And considering both the things, this parameter TEWI is worked out, and the decision about environmental properties should rest upon should be taken based on TEWI rather than GWP. Okay, so these are the environmental properties, A, B, C. Now safety properties. So D, toxicity. The refrigerant should not produce harmful effects when concentration of refrigerant in air and exposure time is small. If the concentration is low and the exposure time is small, even in that case, it should not have any toxic effect on the humans. It should not react with surroundings to produce hazardous chemicals. Refrigerants are divided into two groups according to their toxicity. This is based on an ASHRAE standard. ASHRAE is American Society for Heating, Refrigerating and Air Conditioning Engineers. Right? A similar society in India is ISHRAE, that is Indian Society for Heating, Refrigerating, Air Conditioning Engineers. So class A signifies refrigerants for which toxicity has not been identified at a concentration less than or equal to 400 ppm, while class B signifies refrigerants for which there is evidence of toxicity at concentrations below 400 ppm. So if below 400 ppm also it is toxic, then you need to be alert, and they are put in class B, otherwise in class A. All common refrigerants except ammonia falls in class A. Flammability, the refrigerant should be preferably non-toxic and non-flammable. Refrigerants are divided into three groups according to flammability, again from an ASHRAE standard. Class 1 indicates refrigerants that do not show flame propagation when tested in air at 21 degrees Celsius and 101 kilopascal. Class 2 indicates refrigerants having a lower flammability limit of more than 0.1 kg per meter cube at 21 degrees Celsius and 101 kilopascal, and a heat of combustion of less than 19 kilojoule per kg. Okay, so concentration less than 0.1 is there, and in that case there is no flammability and heat of combustion is less than 19. So they are put in class 2, and class 3 is highly flammable as defined by a lower flammability limit of less than or equal to 0.1 kg per meter cube at 21 degrees Celsius and 101 kilopascal, and a heat of combustion greater than or equal to 19 kilojoule per kg. Right? So even at 0.1 kg per meter cube, it is still flammable, and the heat of combustion is less than 19 kilojoule per kg. Right? So in that case, they are considered to be flammable. And refrigerants like R22, 134A, CO2 fall in class 1, right? So not flammable. R32 and ammonia falls in class 2, while R290, that is propane, falls in class 3. The other properties could also be important. One is chemical stability. Obviously, the refrigerant used should be chemically stable because it has to work in that closed cycle for whatever is the life of the system. Then compatibility with common materials of construction. So whichever material you are going to use, copper or aluminium or some probably plastic materials at joints, etc. So it should not react with those materials, and so that you have to see the compatibility of the materials also. If ammonia system is used, ammonia is not compatible with copper and its alloys, so you have to use only steel in ammonia systems. Then miscibility with lubricating oils. Right? So because you are using a compressor which has moving parts, you need lubricating oil. Okay, so generally it's desirable that the refrigerant and the lubricating oil are miscible. Miscible means they don't separate out okay, significantly. That is desirable in most of the systems. In some of the systems, you may have they may not be miscible, and you may have a separator, oil separator installed after the compressor. Refrigerants that are completely miscible with oils are easier to handle, though it's written R12. R12 is now a thing of past. For refrigerants with limited solubility, R22, special precautions should be taken while designing the system to ensure oil return to the compressor from the refrigeration system circuit. So if you are talking about a system, small system with hermetically sealed compressor, the lubricating oil is going to travel with the refrigerant throughout the system, even in the heat exchangers, the condenser and evaporator. So to ensure that they don't get deposited at certain points in the system. If that happens, then it is not good for the system, because the oil layer reduces the heat transfer. That is one part. And second, if the oil is deposited at other places, the compressor will not have sufficient oil. It will starve of oil, and it can damage the compressor. Right? So you have to ensure that your system is designed such that the oil which is traveling with the refrigerant again comes back to the compressor. Then next thing is dielectric strength, which is important for hermetically sealed compressor, where the refrigerant comes in direct contact with the electrical or motor windings. So it's a electrical insulating property. It is an important property primarily for systems using hermetically sealed compressors, where motor winding is directly exposed to refrigerant. The dielectric strength of fluorocarbons is good. It is 1.31 for R22 as compared to nitrogen, which is assigned a value equal to 1. Okay. Then ease of leak detection. It is difficult to detect leaks in case of CFCs because there is no smell. HCFCs and HFCs, as there is no smell. Ammonia has strong smell, and thus it is easy to detect its leakage. Of course, just the smell is not the only way of leak detection. There are more sophisticated and better ways of doing it. So soap bubble method is one of the primarily used method, and other methods, halide torch methods, are also used in case of hydrofluorocarbons to detect leakage. Electronic leak detector is most sensitive, but its use is generally limited to manufacturer's facility. So I have been talking about the names of the refrigerants, and they include certain numbers, and you still might not be able to uh, know what those numbers stand for. So now we are talking about various refrigerant families and their designation. How do you give a particular number to that refrigerant, right? So first one, the most common refrigerants are from halocarbon family. Okay, so they have chlorine, fluorine, bromine as their one of the atoms in that molecule. So halocarbon family refrigerants have been one of the most important categories of refrigerants. It is comprised of refrigerants which are non-flammable, and most of them are non-toxic also. But many of them have now lost favor due to their negative impact on environment, like ozone depletion, like R12, R11, even R22, R134. 134A is having zero ozone depletion, but R22, okay. So environment like ozone depletion and greenhouse effect, right? So those which are having zero ODP, like R134A, they still have a high greenhouse effect. So earlier people used to call R134A as eco-friendly refrigerant, but then with the consideration of greenhouse effect, now you should not call it environment friendly refrigerant. The molecules of CFCs such as R11 and 12 contain only carbon and halogens. They persist in atmosphere for many years and eventually diffuse into stratosphere. These CFC molecules break down and release chlorine, which destroys ozone. In the lower atmosphere, these molecules absorb infrared radiation, which may contribute to the warming of the Earth. So that's what is global warming or greenhouse effect. Substitution of a hydrogen atom for one or more of the halogens in CFC, particularly chlorine, in CFC molecule greatly reduces its chlorine and bromine, greatly reduces its atmospheric lifetime and lessens its environmental impact. These compounds are called hydrochlorofluorocarbon HCFCs. If there is only fluorine present in the molecule, it is called hydrofluorocarbon. Okay. So, and then another family can be hydrocarbons. Hydrocarbon refrigerants are natural, Non-toxic considered to be natural. Non-toxic refrigerants that have no ozone depletion potential, so ODP is 1. Absolutely minimal global warming potential, so they are acceptable from point of view of environmental properties, but safety properties are of concern. In 2007, the parties to Montreal Protocol decided to accelerate phase out of HCFCs, a group of ozone depleting substances with high global warming potential. Most low GWP alternatives to it are flammable. So these hydrocarbons are flammable to various extents and therefore require appropriate precautions when you manufacture the system and when you operate the system. Hydrocarbon HC refrigerants have a negligible global warming potential and do not produce noxious fumes if they catch fire. It is important to avoid unnecessary accidents due to ignorance and neglect while using the hydrocarbons as refrigerants, as they are flammable. Hydrocarbons are flammable and may not be safe to be used in, for example, say automobiles. Hydrofluoroolefin like HFO-1234YF, which is tetrafluoropropene, has been proposed to replace R134A in automobiles. It has GWP of only 4 and it is only mildly flammable. So this HFO-1234YF is marketed by Honeywell, and it is proposed to be one of the eco-friendly refrigerants, but I believe it has to still prove itself for longer durations. Some of the CFCs, HCFCs and HCs are mentioned in the following table. So one table is will be shown now, and their designation, chemical formula, name, etc. are given. Now, when I use certain number like R12 or 22 or 134A, what does that mean? So it's RABC basically, right? 1, 2, 3. So ABC. Number of carbon atoms, if there is an A, the first digit, which is 0 many times. So if you add 1 to that, it shows number of atoms, right? So if there are only 2 digits, it means that it is some kind of methane compound, right? So it is A plus 1 is number of carbon atoms. Then hydrogen atoms is this digit. So B minus 1, right? So if it is R12, so B is equal to 1. So in that case, there is no atom of hydrogen in that. And fluorine atoms are equal to C. So when I say R12, there are 2 fluorine atoms and remaining are chlorine atoms. Okay, so this thing has been shown for this R22 or HCFC22. So there is 0 here, so that it has 1 carbon atom. And this is 2, it means 2 minus 1, there is 1 hydrogen atom, and there is 2, it means there are 2 fluorine atoms. So this table gives you the designation used, common designation used, chemical formula for that refrigerant, chemical name of that, and some information about that, right? So R11 is trichloro monofluoro methane. It was used in large capacity centrifugal chillers. Evaporator would work in vacuum. In this case, it is phased out due to high ozone depletion potential. And R12, so there are 2 fluorine in this, and difluoromethane, right? So that's the, sorry, yeah, methane. So small capacity unitary equipment phased out due to high ODP. R22 is monochloro difluoro methane, right? So, and the use is in central AC food freezers, and it has low ODP 0.05 but high GWP, right? So this is also losing favor and is going to be phased out. R123 is dichloro tetrafluoroethane, So now it is ethane because this is 1. It means that there are 2 carbon atoms. Centrifugal chillers, low ODP, low GWP, right? So in a way, like there were people who were advocating R123 because the ODP is not very high and GWP is also low. But now even this ODP is not considered to be acceptable, and this will also not survive long in market, or will be phased out to a great degree, or yeah, or phased down. R134A is tetrafluoroethane and it has 0 ODP but high GWP. Domestic refrigerator, automobile, air conditioning. R290 is basically propane and used in industrial refrigeration, very low GWP. So because these hydrocarbons are flammable, they many times are not used, not considered good for domestic applications or commercial applications. But in industries where there can be extra precaution taken, and the like it can be attended better, so it may be used there. Then R32 is methylene fluoride and small AC equipment, no ODP. So some of the air conditioners are now using R32 and it has moderate GWP 716 still. R600A is isobutane and domestic and small commercial refrigerators and 0 ODP, very low GWP. Okay. Now there is another class of refrigerants also which are basically mixtures, and they are called azeotropes and zeotropes. So azeotropes are those mixtures of 2 or more substances which behave as if they were compounds, for they cannot be separated into their components by distillation. So azeotropes like behave like compounds, and azeotrope evaporates and condenses at a single as a single substance. So when even though it's a mixture, the evaporation and condensation will occur at constant temperature. There is another class of mixtures which is zeotropes, and here they don't exactly evaporate or condense at the components don't evaporate or condense at the same temperature, but there is a temperature rise or drop in the evaporator and condenser. So this is called glide. The temperature change occurring across the condenser or evaporator is called glide. So zeotropes have glide. Azeotropes are designated with 500 series. Zeotropes are designated with 400 series. And so 404 is a mixture of R125, R143A, and R134A. And it's a azeotrope, means it will boil and condense at the same temperature in evaporator and condenser. R503, which is a mixture of R23 and 13, is a zeotrope. Right? It means that there will be temperature change across the evaporator and condenser. Most of these refrigerants have high GWP, though ODP is generally 0. So some information about these azeotropes and zeotropes are given. R404A, it is less efficient at medium temperatures. Only 1 degree Celsius glide is there, so it's nearly azeotropic. 407C it is drop-in replacement for R22. Means if you don't want to use R22, then in the same equipment you can charge it with R407C and use it. But the glide here is high and difficult to maintain refrigerant proportions in case of leakage. R410A is attractive. It has attractive thermodynamic properties. So some of the refrigeration system use these refrigerants also, and it is high in energy efficiency, but the operating pressure is double of R22. Then 507A, industrial and commercial refrigeration, food processing, cold storage, ice skating rink. R508B, very low temperature applications like environment chambers, biomedical freezers, etc. Now there is another class of refrigerants called inorganic refrigerants, like air, water, CO2, ammonia. And they may be called natural refrigerants also. They are also becoming popular, particularly ammonia. And now even in the airport air conditioning, in many of the European countries, ammonia is being used as a refrigerant. So inorganic refrigerant, they will start with 7, and the last 2 digits will be nothing but the molecular mass of that substance, right? So if you are talking about ammonia, it is R717. It's used in industrial refrigeration and also in absorption refrigeration system. Water 718, used in absorption lithium bromide water absorption refrigeration system. Air R729, aircraft refrigeration liquefaction of gases. R744, carbon dioxide, low temperature cascade systems or transcritical cycle dry ice is also used as coolant. Right? So this was a brief about the refrigerants, their applications, the important properties of the refrigerants, etc. And the scenario, as I told you, is very dynamic, and things are changing very fast. The natural refrigerants were the ones which were used initially, but then they were replaced with the synthetic refrigerants. But then these natural refrigerants, because of low GWP and zero ODP, many of them are again getting favor, like hydrocarbons and ammonia and carbon dioxide. Okay.